Hello and welcome to my answers to the OCR Specification A AS paper called Depth in Physics from 2018. So this was the second of two papers and it was out of a total of 70 marks. So let's get started with question 1. So this question had a velocity time graph and it showed a car which was stopping, and it includes both where there's a constant velocity and also the point where the brakes have been applied and then it comes to a complete halt. So which feature of this graph shows the deceleration? And it's important here to note we're looking at something which is slowing down, so it's a deceleration. And also, why is this deceleration constant after 1.5 seconds? Well, the thing that shows it's a deceleration is that there's a negative gradient. And you've got to recall that the gradient of a velocity time graph is equal to the acceleration. And the other thing to show that it's constant is that it's a straight line. So it's these two features, the straight line and the fact it's negative, that show that there's a constant deceleration of that car. Now it says here that the car driver applies the brakes at a distance of 20 metres from the stop line at a junction. Calculate the distance that the car travels relative to the stop line when the car comes to a stop. So if they're applying the brakes at a distance of 20 metres, we're looking at this point here on the graph, and therefore to look at the distance travelled, we're going to be looking at the area under this line over here. So again, the area is just going to be equal to half the base times the height. The base is equal, well, it goes from 1.5 to 4.5, so that's a distance of 3.0. And the height, if that's 10 and that's 15, this must be 14. Now 3 times 14 is 42. Half of 42 is equal to 21. So the total distance that the car travels after the brakes have been applied is 21 metres. But that was at 20 metres before the stop line. And therefore, if we look at the distance, it's going to be 21 take away 20, which equals 1.0 metres. So the answer for part B here was just equal to 1.0 metres. And I think a few people maybe forgot to... I think a lot of people worked this out correctly as 21 metres, but they forgot to take off 20 to get the distance from the stop line at that junction. Question 2 was about what you could do in the lab to work out the efficiency of a small motor a bit like this. So this is something that you might have done already in the lab, but I think the key thing here is that you've got to draw a suitable diagram. Now, one of the diagrams might be you've got some kind of power source, we've got maybe an ammeter, and then we've got the motor. So this is my motor with an M in it. And what we can do is we can put a voltmeter across this to measure the potential difference. So this is very much a very simple circuit diagram. And you can always label it if you're not sure about maybe the symbol for a motor. So that is the motor in there. And I think the other things are fairly straightforward. And then what you do is you'd have this motor set up maybe with a bit of string, and then you've got a mass over here. So maybe this is our mass, this is the motor again, and you maybe have this on the edge of a bench. And again, these are just quick sketch diagrams, but what you can do is label different bits and pieces. So what we have is a motor set up at the edge of a bench. We've got a piece of string that goes to a mass. So what we can do is we can take some measurements. So for example, we might measure the mass using a balance, or a mass balance. We can look at things like the height that this goes through using a ruler, and we can time how long it takes to go up a certain distance using a stopwatch. And current and PD can be measured with ammeters and voltmeters. Now this stuff here seems really obvious, but you've got to make it very clear the measurements that you're going to be taking and actually what you do to take those measurements. And you can also include information, for example, that the ruler might be clamped vertically, and you can use a set square to make sure that you've got the vertical height that you're measuring. It might be that you're making sure the balance has been zeroed before you put the mass onto it. So what we're looking at are the measurements and then some of the equipment that we're going to be using. Now for this one here, we can look at the energy transferred to the mass as it goes up through a certain height. So we might say that the energy transferred is equal to the power times the time, which is I, V, and T. So that lets you look at the energy transferred to the motor. But we can also look at the energy gained by the mass as it goes through a certain height. So this is going to be equal to mgh. So maybe that's the energy in, and that's the useful energy out. And what you've also got to do is, again, just put down things like the equation that we can use for efficiency. So we know that the efficiency is going to be the ratio of the useful energy transferred divided by the total energy in, and this is going to be equal to mgh over IVT. So it's worth setting out these equations. And what I've got here are diagrams that kind of show the setup. We've got the apparatus that we're using to take these measurements, and then we've got some equations that show how these measurements are going to be used. And again, when it comes to setting up your answer, bullet points can be useful, and you've got to make sure to get the 6 points that you've written a clear, logical description of how you carry out this experiment. And also, there are other things here, for example, how it can be safely conducted. So it might be that underneath the mass you have a cushion or some kind of foam or something that meant that if this falls, it's not going to damage the floor or the masses. And maybe just put in some other safety considerations, maybe like just making sure that you don't put your hands underneath the mass as it's rising up. So this question here, it's straightforward stuff that you will have done before at some point, and it's just a case of just thinking logically, making sure that you cover all of the basic bits of information in order to get the full 6 marks for this question. In this question, we had a small steel ball that was dropped from rest from different heights, and then the time it took to land was recorded. So, how could the student use standard lab equipment to make accurate measurements of h and t? So first of all, let's think about the height. What we want to do is use a ruler, and to make sure the height is as accurate as possible, you've got to include things like maybe using a set square to make sure that it's vertical. It could maybe be clamped in a clamp stand or a retort stand. And also we maybe think about our eye level to reduce any parallax error. So these are the kind of things that you can talk about how to get an accurate measurement of height. Now when it comes to the time, what we've got is the time measured to 3 significant figures. So that's probably more than you get with just a normal stopwatch. So the way to do this in the lab, because we're using standard lab equipment, is some kind of electronic timer or data logger. So you've got to mention about how we can use a data logger or an electronic timer. And what we're then going to think about is, to get the other couple of marks, how do we start this and how do we stop it? So what you might have is, and a lot of you will have probably done this experiment, where you've got an electromagnet holding the steel ball at the top. When that becomes demagnetized, the ball drops, it starts the timer, and then it goes through a trap door at the bottom to stop the timer. So what we might think about to start the timer is we have an electromagnet, and at the end we have a trap door. So that's a standard way of measuring this time. Equally, we could have used light gates. And you can have a light gate at the top to start the timer and a light gate at the bottom to stop it. Light gates on their own is not the answer, because the light gates need to be connected up to the data logger to actually record that data. So for this one here, there were 4 marks available. In the table, complete the missing value of t squared. So this one here, we've got the value of t. So we've got 0.43, we square that, and the answer is 0.185. And it's important here that we give that answer to 3 significant figures, like all the other data in that table. So 1.85 is the answer for that. We're then going to look at some data. So we've got h on the x-axis, t squared on the y-axis. So we're just going to plot the missing data and draw in the straight line of best fit. So the point just goes there like that. And when it comes to drawing my line of best fit, I'm going to be using a pencil and a ruler. 30 centimetre rulers are really important, and if you've got a clear one, you can see that there's going to be approximately the same number of points above and below the line. I think that's pretty good, so I'm going to do a long line there. So that is, I think, an appropriate line of best fit for that data. Now when it comes to determining the gradient is going to be equal to the change in y by the change in x value, and I'm going to make sure that I take points on the line. So what I'm going to do actually is just draw a triangle to show how I'm doing that. So I'm going to go from the top point up here, doing a nice large triangle, and that's going to go across the bottom as well. So your triangle that you draw, and it is worth drawing the triangle onto the graph, has to be bigger than half the length of that line. So the coordinates up here, so the y value is 0.20, and we're going to take away the y value down here, which isn't 0, but it's 0.13. and we're going to divide that by the x value, which is equal to 0.97, and we're going to take away this value here, which is equal to 0.64. So it's just worth taking time to actually make sure you've got the right coordinates here. So 0.2 take away 0.13 divided by 0.97 take away 0.64, and this gives me a value of 0.21. Okay, so I think that to two significant figures is an appropriate answer to give my gradient. So now we're going to use some SUVAT equations to show that this relationship is true. So for the ball which is dropping, I'm just going to write down S, U, V, A and T. Now the height that it drops through, the vertical displacement S, is going to be called h. We know that it was initially at rest, so U is going to be 0. The acceleration is due to free fall, so that's going to be equal to g, and T is just T. Now we're not concerned with the final velocity at this point. So which equation can we use that doesn't have a v in it? The one we're going to use is S is equal to ut plus a half at squared. So that's my SUVAT equation. We're then going to start realising that basically u is 0, so this term goes to 0. I'm going to replace the s with h. That's equal to a half times a, which is g, times t squared. And because we want to make t squared the subject, we're going to multiply both sides by 2. So we can say that 2h is equal to gt squared. And then we can say that t squared is equal to 2h over g, which is the equation that we have up here. So that's just showing where this equation comes from. Now, use your answer to C part 2. So we found that the gradient m was equal to 0.21, and that's what we found from the graph. Now, whichever value you've worked out, that's the value you're going to use. So this is the gradient. But the gradient, because it was the change in y by the change in x, was equal to t squared divided by h. Okay, but it also says over here that t squared is equal to 2g times h, and that means t squared over h is equal to 2 over g. So what we're really saying here is that our gradient is equal to 2 over g, and that means that g is going to be equal to 2 divided by our answer for the gradient. So I've still got the gradient saved on my calculator here. So 2 divided by the answer gives the value of 9.4. So using my value for the gradient, I've got the value for g as 9.4 meters per second squared. And that's kind of what we're expecting. It's going to be a value in the order of 9.81 meters per second squared. So for question 4, we've got a large diagram with lots of information, lots of numbers. And what we need to do is show the tension in the cable is about 460 newtons. Now this thing here is an equilibrium. That means there's no resultant force acting on it, and there's also going to be no resultant moment. Now what I'm going to do underneath this is just draw my own diagram to hopefully make things as simple as possible. So this is going to be my wooden plank, and because it says here that it's a uniform wooden plank, that means we're going to have the centre of mass, or the centre of gravity, in the very midpoint. So at the middle of the plank, what we have is a vertical force downwards, and it says it's got a mass of 50 kilograms. So that would have a weight equal to 50 times g. Okay. Now there's going to be something happening at P over here, and in actual fact, if this is at the midpoint, that's going to be 1.2 meters from the end, and if that's 0.5 of a meter, then that means the distance from here to here is equal to 0.70. So I'm just drawing my own diagram to make it as clear as possible. Now at 1.5 meters, so this is now a distance of 1.5 meters, again going from P, and again this is just a sketch diagram, it doesn't have to be perfect. This is where the tension is acting. Okay, and here we've got T at an angle of 30 degrees. Now to work out the size of T, which is what we're trying to do here, what we can do is basically say that the clockwise moments are equal to the anti-clockwise moments because this thing is an equilibrium. And of course, the moment is equal to the force times distance. So about point P, let's look at the clockwise moments. So the clockwise moments are going to be equal to the force, which is equal to 50 times 9.81, multiplied by the distance from the point P, times 0.70. And that's going to be equal to the anti-clockwise moment, so stuff going this way round. And that's going to be equal to the force, which is going to be equal to T something 30. So if you're not sure if it's cos or sine, effectively we're looking at the vertical component of T acting at 1.5 meters. Now that means it's effectively the same as this side here, and that's like the hypotenuse, that's the adjacent, and that's the opposite. So we're looking at the opposite side, and therefore if we know we're trying to find the hypotenuse and we know this angle theta, we're going to be using sine. So that's equal to T sine 30 multiplied by 1.5. Okay, now you could have rearranged this to make T the subject. I'm just putting in the numbers first of all. But what I'm going to do on my calculator is just work out this side over here. So that's 50 times 9.81 times 0.7. So we can say that 343.35 is equal to T multiplied by sine 30 times 1.5. And sine 30 is a half times 1.5 is equal to 0.75. So T is going to be equal to 343.35 divided by this answer, which is equal to 457.8. And what we're trying to do is show that this tension is about 460, so that's about 460 newtons. So it's important to show your answer to more significant figures than was given to us in the question. So this shows I've actually worked this out myself, calculated the right answer, and therefore I've shown that the tension is about 460 newtons. And often, if they've wanted you to find an answer and they've shown you what the answer should be, this number is going to be used in some subsequent calculation. So for part B, we want to look at the extension of the cable, and we're going to be using some stuff from our data sheet. So we've got the Young modulus being equal to stress over strain. Stress is force over area, and strain is X over L. So what we can say is that the Young modulus is equal to the force divided by the area, so that's the stress, divided by the strain, which is X over L. Okay, so this is where we're going to start with. Because we've got F over A over X over L, we can also write this as E is equal to FL over AX. But we want to make X a subject, and therefore X is equal to FL over EA. So X equals Fl. So, do we know the force? Well, yes, because we worked it out in that previous question, so that's the tension in the cable. We know the length up here. We know the Young modulus, and we've also been given the area. So we can just plug the numbers in. So X is going to be, I'm going to use my value of 457.8. The length was 1.73 meters. Then we've got 210, and it's giga, so that's 10 to the 9, multiplied by the area. And here we've got 11.0 times 10 to the minus 6. Now this is a mistake that lots of people make. Because we've got millimeters squared and we're trying to convert to square meters, you've got 10 to the minus 3 squared, which is going to be 10 to the minus 6. So these are numbers we're going to use, which gives a total answer equal to 3.43 times 10 to the minus 4. And I suppose in this question here, this data was given to 3 significant figures. I suppose the fact that we got the tension based on data from 2 significant figures means that I guess really we should give the answer as 3.4 times 10 to the minus 4 meters, but either of these were fine for this question. So let's look at question 5 next. Now I thought that question 5 started with an easy definition. This is something that you just have to remember. And Newton's second law says that the force is proportional to the rate of change of momentum. Okay, that's all there is to it. Now, if you put down F equals ma, that is not the correct answer. So that only is valid when you've got a constant acceleration and a constant mass. So F equals ma is only a special case. Newton's second law should be defined as force is proportional to the rate of change of momentum. Now, you could have said something like F is proportional to delta P over delta T, but if you did that, you'd have to make sure that you define the terms. So you could say this equation where F equals the force, P is the momentum, and T is the time. And I think only about 50% of candidates scored this 1 mark, which is a real shame. Okay, the next question is about a tennis ball that hits the ground and then bounces up again. And it says the mass of the tennis ball is 0.062 kilograms, and it's travelling at 14 metres per second. So we want to know the momentum of the tennis ball as it hits the ground. So at this instant here, momentum is going to be equal to its mass times its velocity, which I'm going to call u because it's its initial velocity here. So that's going to be equal to the mass of 0.062. Its velocity was 14 metres per second. And this gives the momentum equal to 0.868. So the momentum was 0.87 Newton seconds. And I guess if this is a positive direction, then that's also then going to be a positive momentum. For this part here, we then want to look at how quickly that tennis ball rebounds as it leaves the ground. So what we want to look at, I suppose, is its change in momentum, because its change in momentum is going to be equal to the force applied times the time for which it's acting. Okay, and we know the time in collision with the ground is 0.18 seconds, but actually on a previous page we find that the force was not constant. So the force increased and then decreased. And in order to work out the change in momentum, we're going to look at the area under this force time graph. Okay, and this then gives us the impulse that's been provided. And that means the change in momentum, delta P, is equal to 1.53. Now, we want to find the final momentum, and that's going to be equal to the initial momentum, take away the change in momentum. And in the first part of the question, we calculated that this was equal to 0.868. We're going to take away the change in momentum, which is 1.53. And this means that our final momentum is going to be equal to minus 0.662. So that means that it's now got a momentum in the upwards direction. Of course, momentum equals mass times the final velocity. So the final velocity is going to be the momentum, which is minus 0.662 divided by the mass, which is 0.062. And this gives a value equal to minus 10.7. So to two significant figures, this is going to be a velocity of minus 11 metres per second. But because we're looking at the speed, we just want to know the magnitude. So I'm just going to leave this as a positive value. So effectively, the tennis ball comes in at 14 metres per second and it leaves at 11 metres per second. And then I guess that leads on nicely to this question here. What is meant by an elastic collision? And explain how your answer to question 2 up here shows that this collision is not elastic. So for an elastic collision, we can say that momentum is conserved, and so is kinetic energy. And of course, like everything, energy is also always conserved as well. So for an elastic collision between two objects, not only is momentum conserved, but the total kinetic energy is conserved as well. Now, why is this collision not elastic? Well, what we can say is that I suppose the final value for the velocity is smaller than the initial value for its velocity. So what we can say is that the speed decreased, and that meant the ball transferred some of its initial kinetic energy, and you might say to the thermal store. So for this one here, we're really looking at our definitions for elastic collisions where kinetic energy is conserved. But here, because when it rebounded with a lower speed, despite having the same mass, it meant it must have had less kinetic energy afterwards, and that meant some of the energy was transferred into heating up the ball and the surroundings. So question 6 had the IV characteristics of two components, and I guess normally we see them a bit like this. So what are components X and Y? Well, X is something that looks a bit like this, which you should recognise as a filament lamp. So X was a filament lamp, whereas Y had this constant line, and that meant it could either be a resistor or an ohmic conductor. Then underneath it we had our battery, which has an internal resistance, but it's got an EMF of 9.6 volts. And it says here we've got elements X and Y in parallel and a voltmeter just reading the potential difference across each of these. So the question for part B said that the voltmeter reading is 7.2 volts. Determine the value of the internal resistance. So I'm just going to label it on my diagram. That's going to be equal to 7.2 volts. Now, in order to work out this resistance here, we need to maybe look at the current flowing in the circuit. And if that potential difference is 7.2 across X and Y, what we can do is use the graph above to read off our values for I at different times. So that's 7, that's 7.2. So I'm just going to use the graph to carefully read the values of the current, which we can do from over here. So at this point, the current in the current in X, first of all, is going to be equal to 0.50 amps. And the current in Y at this time is equal to 0.36 amps. So we've got the current at two different parts of the circuit, and by Kirchhoff's first law, we know that the current here, I, is going to be equal to the current at X plus the current at Y. So the current at this point in the circuit is equal to 0.50 plus 0.36, which is equal to 0.86 amps. Now the other thing we might recognise, if that's 9.6 as the EMF and there's 7.2 volts there, we can also think about effectively the lost volts across the internal resistance of that battery supply. So that's going to be 9.6 take away 7.2, which is going to be equal to 2.4 volts. So to work out the value of this resistance, it's going to be the lost volts, which are equal to 2.4, because R equals V over I. The current is 0.86, and that gives a value equal to 2.79. So again, to two significant figures, like some of the raw data, we can say the internal resistance of this power supply is equal to 2.8 ohms. Now for the next one, how could the student measure precisely the diameter of the wire? So what we're going to think about here is using some kind of micrometer or caliper, and that will get you a good reading. But what you've got to do is you've got to do it 3 times. And we're looking at, if you have that strand of wire, measuring the diameter in at least 3 different places. And once you've done that, you can then take your mean value of those. So what we're looking at is you've got the equipment you're using and then how you use it. So you're taking 3 readings to get the mean value. Okay. For the next question, we want to determine the resistivity of copper. Now, resistivity is going to be equal to RA over L. Now, in this question here, we've got the total resistance of the whole cable as 1.86 plus or minus 0.2 ohms. Now, if that's the resistance of the whole cable, but there are 17 strands, then effectively what we have there are 17, it's a bit like having 17 resistors in parallel. Now the more resistors you have in parallel, the lower the combined resistance, and if all of these are the same type of wire, that means the total resistance is going to be equal to 17 times the total resistance of that cable. So that's going to be equal to 17 times 1.86 to get the total, that's going to give you the total resistance of one of those strands of wire. The other thing here is it says that the diameter of the wire is equal to 0.12, and therefore to work out the area, that's going to be equal to pi r squared. So this is going to be equal to pi times 0.06 times 10 to the minus 3. So that's my radius, not the diameter, because they often give you the diameter. I'm going to use the radius here, convert it to meters, and that's going to be squared. So that's going to give a value equal to 1.13 times 10 to the minus 8, so really small areas, and the length is equal to 21 meters. So the resistivity then is going to be equal to 17 times 1.86 times, so that's the resistance of a wire, because it's 17 times the resistance of that whole cable, times the area, so 1.13 times 10 to the minus 8, divided by the length, which is 21.0. And this gives me a final answer of 1.70 times 10 to the minus 8. And for this one here, we can give our answer to 2 significant figures, like the diameter that we use to work out the area. So that's going to be equal to 1.7 times 10 to the minus 8 ohm meters. And that's the kind of value we tend to get for resistivity. It's going to be in the order of 10 to the minus 8. We then want to look at the percentage uncertainty in this resistivity. So we're going to do that by looking at the percentage uncertainty in R, in A, and in L. Now in R, it's going to be equal to 1.8, sorry, it's going to be equal to the uncertainty 0.02 over the measured value of 1.86, and multiplied by 100, that would be equal to 1.07%. The uncertainty in L is going to be equal to 0.1 over 21.0, which equals 0.48% uncertainty. And the uncertainty in the diameter of the wire is going to be 0.01 over 0.12, which equals 8.33%. So the uncertainty in R, the uncertainty in L, and the uncertainty in D have just been calculated. But to work out the uncertainty in the area, it's going to be equal to D squared, or R squared. And that means we've got to double this uncertainty. So the total uncertainty is going to be the uncertainty in R plus the uncertainty in A, which is 8.33 plus 8.33. And then we're going to add on the uncertainty in L, so 0.48. And this gives me a value equal to 18.21%. So I'm going to give this to two significant figures. So that's going to be equal to 18% uncertainty. And we can see here that most of the uncertainty came when it came to actually measuring the diameter of that very small wire. So that's how I've done it. I've just done my calculations for the uncertainty in the different values and then added them appropriately at the bottom to get the combined uncertainty in the value of the resistivity. So for question 7, we have a microwave transmitter, the kind of things that you might have used at school. We've got a metal sheet, and what we're doing is that we're sending a signal from this. It's going to hit the sheet and it's going to bounce back. And then we're going to have regions here where we have destructive and constructive interference. And as D is moved, we're going to get maximum and minimum values. And it says here that distance between adjacent regions of maximum and minimum intensities is 72 millimeters. And we need to explain why this actually occurs and also determine the frequency of the microwaves. So I might do the frequency first of all. Now the frequency is going to be equal to the speed of the microwaves divided by the wavelength. Now because these are electromagnetic waves, the speed they're travelling at is going to be equal to 3.0, well, it says in the question as well, doesn't it? 3.0 times 10 to the 8. I mean, you knew that anyway, didn't you? And the data's in the data book. In terms of the wavelength, well, effectively, if you've got a maximum and a minimum intensity, this is a bit like a antinode and a node for a stationary wave. Now, the distance from a node to a node is half the wavelength, so the distance from an antinode to a node is a quarter of the wavelength. So what we can say is that the wavelength, a quarter of the wavelength, is equal to 72 times 10 to the minus 3 meters. So that means the wavelength is going to be 4 times this, which is equal to 0.288 of a meter. Okay, so about 30 centimetre wavelength for these particular microwaves. So that's just going to be equal to 3 times 10 to the 8 divided by 0.288. And that then means that the frequency is equal to 1.04 times 10 to the 9. Okay, so that's going to be our frequency in hertz. So that's a relatively straightforward calculation, but I suspect a lot of you might have forgotten that from an antinode to a node is a quarter of the wavelength. So what's actually happening? Well, this is where you've got to think about your structure, about kind of, I guess, telling the story of the microwaves, and then thinking about the kind of key technical terms that you want to get into your answer. So you might have said something in the order of the fact that microwaves are reflected by the metal sheet over here, and then they interfere with other microwaves leaving the transmitter. So that's kind of what's going to set up this standing wave. And this standing wave is formed due to the superposition of these waves. So think about some of these kind of technical terms that we can get into our description. We then have areas of constructive interference, which cause a maxima at an antinode. And I guess opposite to this, we get destructive interference causing minimum intensity at a node. So all of these kind of good wave terminology bits and pieces in your answer. And then I guess you can also say things like that the node to an antinode is a quarter of a wavelength, which is why we then get to this answer over here. So for something like this, there are so many questions in other past papers, asking you to describe how a standing or a stationary wave is set up. But this one here just happens to be using microwaves. We then have something else that you will have seen in the lab where you've got a metal grill, and as you rotate this, it says here that it goes from 0 to a maximum and back to 0, again, if we look at the intensity measured at D. So why does the detected signal behave in this way? Well, first of all, when you've got a microwave transmitter, it emits plane polarised waves. And this is an important first point to say. What we then have is, as this is rotated, we're going to have some points where all of the waves are blocked, which is what it's initially. As it's rotated, it then starts to let the waves, the plane polarised waves through, and then as it goes to the final position, again it causes no more of these plane polarised waves to be transmitted through it. So at 0 and 180 degrees, the grill is blocking all the waves, but then it allows them through at 90 degrees. And this is because the waves which were emitted initially were plane polarised. So in question 8, we've got some light which is going to be refracted as it goes through different mediums, including glass and ethanol. And we've got a table first of all where we just want to complete some values. Now effectively the refractive index tells us how much by sort of what factor the light is slowed down by. Now effectively if the light has been slowed down from 3 to 2.2, we can work this out as 3 divided by 2.2. It slows down by a factor of 1.3636. So here the refractive index is going to be equal to 1.36 to two significant figures like the rest of the data. That means then for glass, if it was travelling initially at 3 times 10 to the 8 and it's now been slowed down by a factor of 1.52, we're just going to have 3 divided by 1.52 to give an answer of 1.97 times 10 to the 8. So that means that that's going to be the final speed of the light in the glass. Okay, and again to three significant figures like this data, and it's also of course 10 to the 8. Now what we're going to do is calculate the wavelength of light in the glass. Now we know of course that V is equal to F lambda. That's a wave speed equation, but here of course the frequency is going to be constant because the frequency of that light doesn't change as it goes from one medium to another, and therefore we can say that the velocity is going to be proportional to the wavelength. Now in glass it's going to be 1.97 of its original value of 3 times 10 to the 8, and that means the wavelength is going to be shortened by the same factor. So what we can say is that 1.97 divided by 3.00, and again these are both 10 to the 8, but because we're dividing, I'm just going to leave out the 10 to the 8. So this is how much shorter they're going to get, and we're going to multiply that by the wavelength, and it says in the equation the wavelength is 5.2 times 10 to the minus 7. So that's going to be equal to 1.97 divided by 3, so 0.65 times 5.2 times 10 to the minus 7. Means that the final wavelength is going to be equal to 3.415 times 10 to the minus 7. So that's 3.4 times 10 to the minus 7 meters. So what we've seen here is that the factor that the light slows down by, going from 3 to 1.97, is the same factor that the wavelength goes from a longer value of 5.2 to a shorter value as it goes through that denser medium. So that's 8 part A. So in this diagram we've got the light coming in at 37 degrees and it's going to go into initially the glass. So what angle of refraction theta is in the glass? Okay, now it does say in your data sheet that n sine theta is going to be a constant. Okay, so again these are the equations that we can use for refraction. So if n sine theta is a constant, then we can say that n glass sine theta glass is going to be equal to the value for the air. So NA for the air times sine theta in the air. Okay, so this is the equation I'm going to use. So that means we're trying to find this value here. So we're trying to find this value here, the angle of refraction in the glass. So what we can say is that sine theta in the glass is going to be equal to the value for n in the air, which equals 1.00 times sine 37 divided by n for the glass, which equals 1.52. And then we're simply just going to put the numbers into the calculator. So sine theta is 0.3959. Inverse sine of that answer gives a value of theta in the glass equal to 23.3 degrees. So 23 degrees. And again, that seems appropriate because it's going to be smaller, because as it slows down, it's going to bend towards a normal, and therefore the answer we're looking for should be smaller than that 37 degrees that we initially had. And then, without further calculation, sketch the ray of light as it passes through the glass into the ethanol. For this one, I'm going to be using my pencil and my ruler. I'm just going to estimate that this angle here is about 23 degrees. Okay, so I've done that first ray of light like that. And to help me with the next bit, I'm just going to do, again, a normal to help with my diagram. And from the table of data, we see that in ethanol, the value of the refractive index is between air and glass, which means it doesn't slow down even more and bend even more towards the normal, but it speeds up, but not as much as if it was going into air. So that means the ray of light that we draw now, it can't be parallel to the ray of light, so it can't be at an angle like this, and therefore I'm going to draw it at an angle a bit like that. Okay, so it bends the most here, and then it bends back, but not so much to be parallel to the ray of light that goes in. So that's how I get the 1 mark for question B, part 2. And the last question, question number 9, is looking at the photoelectric effect. So we're going to define the following terms, so not just state what they are, but what they actually mean. So HF is the energy of the incident photon, so that's what HF means, and phi, the work function, the minimum energy required for an electron to escape from the surface of the metal. So the work function on its own doesn't exactly define what it means, so that's why you've got to write these definitions in. We then got this next equation here that says we've got some radiation which has this frequency. It's the work function of aluminium is 4.1 and it's given in electron volts. And we want to show the maximum speed of the electrons emitted is 5.5 times 10 to the 5. So lots of stuff there to do. The first thing I'm going to do is convert the work function from electron volts into joules. So 4.1 electron volts, we're going to multiply this by 1.6 times 10 to the minus 19 to get it into joules. And that's a value of 6.56 times 10 to the minus 19. Now, we're going to look at the kinetic energy, and what we can say is that HF minus the work function is going to be equal to the maximum kinetic energy, which is what we're trying to calculate. So H is given as 6.63 times 10 to the minus 34, and that's given to you in your data book. We're going to multiply this by the frequency of 1.2 times 10 to the 15, and take away this value here that we've just worked out as 6.56 times 10 to the minus 19. That's going to give the maximum kinetic energy, which is equal to 1.396 times 10 to the minus 19. Now, of course, the kinetic energy is equal to a half mv squared, and v is equal to 2ek over m square rooted. So that's going to be equal to 2 times 1.396 times 10 to the minus 19 divided by the mass. And if they're electrons, their mass is 9.11 times 10 to the minus 31. All square rooted, and that gives me an answer for the velocity of 5.536 times 10 to the 5, which is actually what we're aiming for up here, 5.5. So that's equal to 5.5 times 10 to the 5 meters per second. And again, it's important to maybe show your answer to maybe 4 significant figures to show that you've actually carried out the calculations, because again, this is a show me question. For 9, part 2, it's 2 marks. What happens to this value if the intensity of the EM radiation is induced? So you're shining more light but at the same frequency. Well, it's important to state that the kinetic energy is independent of intensity. So you might have more photons landing, but each photon is still only going to be absorbed by 1 electron, which will travel up to this maximum velocity. And therefore, what you could also say that maybe the number of photoelectrons emitted increases, but the ones that are emitted, they're not going to be travelling any quicker. And finally, the last question, again, this kind of comes up in many forms in other past papers. We know that electrons have wave-like properties, and we want to know the wavelength for electrons travelling at this value. Now, again, the wavelength is going to be equal to h over mv, so Planck's constant and the momentum of those electrons. So that's going to be equal to 6.63 times 10 to the minus 34. M is going to be equal to 9.11 times 10 to the minus 31, the same value that we had in the last question. And here the velocity is going to be 5.5 times 10 to the 5. So this one here, we're just going to put the numbers in. And this gives me a number of 1.323 times 10 to the minus 9. So that's going to be equal to 1.3 times 10 to the minus 9 meters. So that's the last question. I thought that this exam paper had some generally quite nice questions throughout, especially the last question. I mean, if you look at other questions to do with the photoelectric effect and wave-particle duality, they've got very similar questions just with different numbers. So even the last question was relatively straightforward if you've done a lot of practice. So hope that's helped. Don't forget, of course, to subscribe on YouTube and find loads more videos over at A Level Physics Online. Thank you.